Okay, so it's actually the next lecture, but continues the idea of sufficiency. So all this is saying is that there are a lot of sufficient statistics. Once you have one of them, you can make another one just by taking a one-to-one function of it. Let's show this now. So we have T of Y is sufficient for theta, the same setup as the previous lecture. And so if T of Y is sufficient for theta and R is a one-to-one function, then R T of Y is also sufficient for theta. Okay, so show this easy, not underwhelming, I think. So Ly given theta. So T of Y is sufficient, so we can go right to the factorization criteria here, T of little y. And since R is invertible, we can write it like this, G R inverse R T of Y. One more. And theta. And H of Y. I feel like we're done. We just showed the factorization exists, right? I think this is enough. I have in mind we can make this maybe look a little prettier if you want. So we could define T star and G star of, say, UV to equal G R inverse U V. And then we see, using this notation, maybe this just brings it out a little better, that the likelihood is equal to G star of T star of Y theta times the same H of Y. So showing that, so T star of little y equals R T of Y is sufficient. Okay, so since sufficient statistics are good, they contain all the information you could want about the parameter. We would like them to have low variance and be, well, they will naturally have low variance usually. They're good estimators. They should have low variance usually. I'm sure you can find examples maybe where they don't, but they will usually. And but they may not be unbiased, because if you think about the ones we did so far, like for example, the using the sum for the sufficient statistic for P in the Bernoulli sample, sum's really an estimator for the binomial, right? It's NP. So we need a function of the sum that is unbiased for P. And, we just said, since the sum is, the expected value of the sum is NP, we just want to divide the sum by N in that case. So let's just write this down. So we'll say sufficient statistics contain all info in the sample relevant to the parameter. So if we can make it unbiased by taking a one-to-one function, Okay, so we want to make sufficient statistics unbiased. We can achieve this by taking a one-to-one function of a statistic, sufficient statistic from the factorization criterion theorem. Okay, so let's do an example. We'll just write out the Bernoulli one first. So suppose so suppose y1 to yn is Bernoulli P. Then we already found that the sum yi is sufficient for P. So we want a function, a one-to-one function of yi that will be unbiased. So we have since and have call it y bar. Further, the fact that it came from the factorization criterion also generally makes the statistic the best statistic. You can think of sufficient statistics probably that have higher variance. The ones that come from the FC will generally have low variance. For this reason, although not always, and we're not going to get into any more about this in this course, although you can read Casella and Berger chapter 6, we will call, the book calls these MVUEs, so minimum variance unbiased estimators. So we'll just write this as a definition for now for our course. There's a little more to really understand this better, so we don't want to get into this too much, but we'll say sufficient stats that result from factorization criteria that are made unbiased by taking a one-to-one function of them. I probably could have wrote that in a better sentence, are called MVUEs. So that stands for minimum variance unbiased estimators. So in this case, in the example above, y bar is an MVUE for P. Let's do another one. Here we can do two more examples. Well, here's a real short one. We already found an MVUE actually vector for the normal case. So we found that y bar s squared is sufficient for mu sigma squared since it's already unbiased, and you could take it as a definition that the expected value of a vector of random variables is equal to the vector of the expected values. So this is equal to and this is equal to mu. Then so the two stats that we're the most familiar with. Now, just to be clear, this was is sufficient for these, and this was for, because I'm referring to the example above, for IID normal mu sigma squared. Because we sometimes, sure, we use these for all kinds of distributions, so that should be made clear here too. And the other example I was clear. Okay, so we found this is sufficient for this kind of sample for the parameters, both the parameters at a time. And since this is already unbiased, then these are the minimum variance unbiased estimators jointly for both these statistics. And I mean both these parameters. And since and well, all I was going to say is that since these are the ones we're familiar with and we've been using them for normals in many little exercise and problems, now we know there's a lot of justification for that, even more than we've had. Seen consistency and now sufficiency, and finally minimum variance unbiased estimators, sort of the highest medal they can have at this point. All right, let's just do one more for this and then we'll stop. So suppose I have y1, yn, IID, we looked at this already. And we found yn was sufficient for theta. However, yn is not unbiased. Let's just derive this, the expected value of yn. So first we need the density. So the probability yn is less than little y is just equal to, assuming little y is between 0 and theta, this is just equal to, well, we could put all this in, right? So this is just equal to 0. If little y is less than or equal to 0, it's going to be the probability yi is less than or equal to little y to the nth power, because they would all need to be all the samples would need to be less than little y if the max is going to be less than little y, and then 1 if y is greater than or equal to theta. And so taking the derivative of this, we get the density f and little y is just equal to, well, what is this? This would be, so it's just going to be the derivative of this. What is the probability yi is less than, sorry, with respect to y? What is the probability yi is less than little y? It's just little y over theta, right? This is for 0 y less than theta and 0 else. And so then I can take that derivative and I get, this is just equal to, if we take the derivative here, we get n over theta to the n, y to the n minus 1. 0 else. Okay, so E yn is just equal to integral 0 to theta y times n over theta to the n, y to the n minus 1 dy equals 0 to theta n over theta to the n, y to the n dy, which just equals, raise it to the power n plus 1, I get n over theta to the n, and I get y to the n plus 1 over n plus 1, so I have theta to the n plus 1 over n plus 1, which equals theta n over n plus 1. So it's almost unbiased. If n is big, it's very close to being unbiased. But to make it officially unbiased, we see there's a nice one-to-one function. We just multiply it by n plus 1 over n. So so I notice this is a function of the sample is minimum variance unbiased estimator for it. Just take the max, shift it slightly to the right by multiplying by n plus 1 over n, and you've got your MVUE for this case. Okay, we'll stop now. There's one more lecture on this chapter on the method of the maximum likelihood, and that will do it for this chapter 9 in Wackerly. Remember, the references are Wackerly chapter 9. This lecture was 9.5, and Casella and Berger chapter 6.